Okay, so just to tell you what we were talking about last time. So we were discussing probability. I'm just giving you the basics because I imagine in some way or another, even if you haven't taken probability, kind of like the ideas more or less like make sense. Uh, but for any applications, machine learning, like or like 156 or whatever, like you do have to know some probability. So, I feel like at least I have to kind of like uh, if anything, like just so that we have like the same notation when we refer to things. Um, where is my notebook? Oh, here you are. Okay, so let me move this around. Okay, so I was telling you the basics of probability theory for like just like what people refer to usually as like a single random variable, which it just means like you have a particular type of experiment which has certain outcomes and you assign probabilities to the like likelihood of each of those outcomes. Now, there's another notion which is very useful, which is like that of conditional probability. And so kind of like the idea, just to go back to the example we were working with. Uh, so the experiment, right, could have been one of the examples I gave you last time is like, imagine you're about to receive like a 3-digit like binary code, right? So there are 8 possibilities, right? Because it's 2 cubed, right? So the experiment, which I'll kind of like more like draw it in set notation, it would be 0, 0, 0. That's one possibility. The other extreme is 1, 1, 1, right? And then you could have the cases where there's only one occurrence of 1, right? And the cases in the string, like of the message you're receiving, where like there's 2 occurrences of 1, right? So 1, 1, or one occurrence of 0, depending on how you want to think about it. Right. So those are like the 8 possibilities. And in a sense, like there are kind of like the most basic things um you could receive. Um but then you can kind of like break apart or like partition, like this space of outcomes into other more like specific things. So for example, well, you could for example be interested in, let's do you could be interested in all the strings, right? Oh yeah, this one is easy. You could be like, I'm just trying to see which region to draw easily here. So you could be interested in all the strings that terminate on a 0. Okay, so let's call that A. Yes. Uh, Let me see actually. Oh, that's what he had emailed me, and he said, "Oh, I'm going to join on virtually," and I'm like, "What do you mean by?" Now I know what he means. Okay, okay. So let me. Where is the information about the meeting? Show meeting info. Wait. Here it is. So wait? Can you take a screen? If you want to come here, you can take a picture, and then like you can send him like a message. Yeah, yeah.
So you just record this for the sake of recording it?
Well, they get uploaded to YouTube. Remember? Yeah, yeah. But yeah, that way he can join. But the only thing is like I probably won't be. Well, I'll try to be checking the chat, but I'll do my best. So in case he ends up asking it. Um. So right, like so for example, you could be interested in like the strings that end. Well, assuming that you read this message from left to right as typical, like that end on a 0, right? Right. So in this case, as a region of the configuration space or like the outcome space, I think that kind of covers it pretty much, right? And you know, you can kind you could ask, well, what's the probability, right? Like what is the probability that you happen to find like you happen to receive a string that ends in zero, and well, the idea is that if you label the outcomes, right? Maybe this would be the first outcome. This is the second one. This is the third one. This is the fourth one, fifth one, sixth one, and seventh one. Then if you do it that way, then the probability, right? The probability of A, like the probability that you would assign to A would be just like the sum of the probabilities you assign to these individual strings, right? So it would be probability of A, would be P of X1 plus P of X2 plus P of X3 plus P of X4. Right, because like kind of like the idea is that these kind of like correspond to disjoint events, right? So there's no overlap, so like the probability should just be the sum of the individual probabilities. And more generally, if you had like, I'm trying to kind of like say this in a more like set notation kind of way. The idea is that if you had like a subset of the outcome space, right? Like because we're just doing discrete probability, so there's it's a bit easier than like continuous case. If you had like any subset of the outcome space, more generally, if X is just like X1 up to Xm, and A is a subset of the outcome space, then the probability of A would be, the sum of the probabilities of all the elements that happen to belong to A, right? Is that making sense? Kind of like so far so good. Uh, by the way, Ruben, if you want like I will try to be checking the chat, but if you want to unmute yourself, if you end up having like a question, just feel free to do so. Just in case.
Okay.
Yeah, yeah.
Okay. Should I type in the chat or is
I
there
mean,
a better a way to do it?
sometimes it might be just feel free to interrupt me, like, or like, or just type in the chat that you had a question because like, just typing it would take you forever. So like, if,
Okay.
yeah, and then like, I'll be kind of like keeping an eye on whether, you write something. Uh,
Okay.
yeah.
Uh is X the domain of all like outcomes and then we're splitting it based on like
Right, right. So X is all the possibilities for your particular experiment. And then, right, that's what X represents. And then maybe you are interested kind of like in those outcomes that have like a particular property. In this case, like the property was that the message that you are receiving like terminates on a zero, right? And so
okay.
the question would be, what probability would you assign to that subset? And because everything is discrete, right? Like there are only finitely many outcomes. Like, like the natural condition would be that the probabilities should just kind of like be built out of the individual cases. Yeah. Is that making sense?
Right.
Yeah.
Yeah, yeah, that makes sense.
Were you going to ask me something?
You're like X4 or X4.
Oh my God, yeah, it's totally. Oh, yes, like I kind of like labeled them incorrectly, right? Is that what you're trying to say? Oops. So thanks for noticing that. So this one was X4, right? And then let's say that this one is X8. Now I did fix. Is that yes? I'm glad you noticed that. Um, and then okay, and then I mean there's certain things about doing it this way which are kind of like easy to check. No, under this definition, one is that the probability of the entire space should be one, right? Because something needs to happen, right? And that's almost just the same as saying that the probabilities of the different outcomes need to add up to one. Another one is, that the probability of the empty set should be zero, right? Like the empty set being like, I mean, it's kind of more like a technicality of set theory. but it's kind of like that, the empty set is that which has nothing. So like, yes, it makes sense that that should be assigned probability 0. And then more interesting, right, is that that kind of like this, what is it called? Like inclusion exclusion formula, that if you have like a union, right, if you had two subsets, the probability of A union B would be the probability of A plus the probability of B minus the probability of the overlap, right? Which like if you kind of like draw this kind of like in terms of like diagrams and you imagine like the probability kind of like as a sense of like the size of this, like like you kind of like counting the possibilities, and this kind of like makes sense, like because you should subtract the overlap, when there's like a non-trivial intersection. Uh, and of course, this can be generalized to like a union of n subsets or whatever, but we don't really have to be using that too much. Um, okay, now comes to the conditional probability, which is one of the most important concepts in probability theory. So I'm going to explain that next. So okay, so conditional probability, let me write it like this. I'll write it this P, oh no, actually, let me write it like P given A. Right, so the way you read this is the probability of B given A, okay? So this is a probability of B. I don't know if you have seen probably you have heard about the Monty Hall problem, but that's a very fun problem, like in conditional probability, very counterintuitive. But I should probably post like a video about that because it's kind of like fun, like especially because like famous mathematicians would write to the newspaper where he wrote that column saying that the answer was incorrect, and like kind of like they shouldn't let him like kind of like say that I mean, you have to watch it because it's kind of like very counterintuitive, so it's kind of like fun. But yeah, like this conditional probability can be, developing an intuition for it can be kind of tricky. But okay, so the way you interpret this is that you kind of like assume that you have knowledge that A occurred, and so you want to know what's the probability that a B happens given that A has happened, or like that that you found the outcome is within A. So I'm about to kind of like make it a bit more concrete, but this is like the probability of your outcome being inside B given that it is that A has already taken place, or like that A occurred.
Hmm.
So for example, let me kind of like show you what I mean by this. So just to go back to the previous case. So let me copy paste it twice. In my previous case, let's say that A was like the strings that terminate in strings that end in 0, right? And then you could define another condition B. The other B could be, for example, the strings that have an even number of ones, just to give like an example. So B could be could consist of the outcome where the string has an even number of ones. Okay, so what is B in this case? So what has an even number of ones? So, oh, all of these have an even number of ones, right? I should probably color them. So this is what A corresponds to, right? And B, oh no, actually, B is a little bit smaller because like B is like this, right? Like, so there's only even number of ones. There are only three options, right? So that is what B corresponds to, right? And so, you know, the probability, the conditional probability of B given A, right? What is the probability of B given A? That is the probability that knowing that your string ends in zero, what are the chances that it has like, that string happens to have an even number of ones, right? So this is like the probability that the string has an even number of ones. Given that we know zero is the last digit, right? Zero is the last letter or digit. Oh, right, because oh my God, Cecilia, yes, like uh a positive I don't want to draw, let's say the B has right, because zero is an even number. So let's say a non-zero even number of ones. I just don't want to call, like just to not make the yeah. Oh my, or let's say two, you know, a non-zero. Now it looks so contrived. Yeah, because otherwise you're right. Like 000 should have been included. It's just I don't want to color like 000. Like I want to kind of like keep it on its own island. So, um, okay. So the way you think about it is that kind of like the philosophy behind this is that since you are conditioning on A, kind of like the only relevant outcome space is really the subset A. So it's kind of like you pretend that the rest does not exist because you already have information that something in A took place, right? So kind of like you restrict the entire outcome space to just A, not, and then from there you should kind of like think about what are the chances that that you would find something you know with like an positive number of ones, like a positive even number of ones or two ones, because like that's really like the only thing that would happen here.
So wait, is the probability of a given 100%? It's always going to be there?
What's right. The probability of being inside A, kind of like you have to think about it as it becoming 100%, because you have been told it's kind of like you have updated your information about what just happened. So now you have been told that definitely the string that you found ends in zero. So kind of like everything that ended in zero, like everything else kind of like no longer counts as part of the possible outcomes, if you know what I mean. So yes, like A, it's kind of like that's the way you should think about the conditional probability, that now A kind of happens with 100% certainty. That's one way to think about it. And even has two ones. Well, actually, yes, like to kind of make it more clear what you were asking me about. Right. So kind of let's think about what the probability of A given A should be. Is saying, okay, I already know that A happened. right? So if I already know that A happened, what is the probability that something in A will happen? That should be 1, right? Like that should be, you know. So whatever, however this is defined, it should have the property that the probability of A given A should be 1, because it's kind of like now you have entire knowledge, you know, that A did occur. Is that making sense?
Yeah. Yeah, that makes sense because it's like it must occur in that like subspace.
Right. So like kind of like it's kind of like a balloon where you kind of like inflate the subspace to kind of like the entire size of like the bigger space, and then you kind of like push the rest out of like the picture. You kind of like occupy.
Yeah, yeah.
I mean, this is why this is related to measure theory, because like in probability, you kind of like think of probability as giving like a size of the sets in a sense. Um, so yeah, like it's this is kind of like a normalization condition. So okay, and okay, let me write the formula. So the probability of B given A, well, if you think about it, what you should care about is just how much of B happens to be within A. So what you end up doing is kind of like do the intersection, and then you kind of like divide by probability of A, kind of like to have this normalization factor, so that it has, so that like the previous equation happens to be true, right? Because that way, if you put probability of A here, you get A intersection A, which is just A, so you get probability of A over probability of A, that gives you 1. So it's kind of like looking at the like just to make the picture, what I'm saying is you kind of like look at the overlap region, and you kind of like rescale it so that, you know, it happens to be, let me, so what I'm saying is that you kind of like look in this particular case of with the two, you know, with the two ones, you know, in this region, what has two ones? Only this event has two ones, right? So you kind of like only care about the overlap, and the overlap is like A intersection B. So you find the probability of that, but then you rescale it by the probability of A, so that, you know, because you need to take into account that you know, only A matters now, basically. Is that making sense? Kind of like reasonable.
Mhm. Is is the conditional probability like if I reversed B and A like to like A B, would it be like a different probability because it's on
Oh,
different
right.
conditions?
It is like this is like these are. I mean, probability theory is really fun, actually. Okay. So, what is a classical example? Like, you know, like which one did you say? Right. No, but I'm trying to do something a bit more, you know, less like more like with genetics or something like that. I'm trying to think about it with these examples with cats or no, but they're definitely, you know, I mean, in this case, you can kind of like see it. Oh, I mean, let's just do it in here, like picture wise. You know, what would be the probability of B? Sorry, let's reverse it. What is the probability of A given B, right? So now I know for a fact that B occurred. So now I know that my message oh, is this going to be going to this? Now my message ends up oh no, okay, this one I don't like because it does happen to coincide. So what would be an example here where it doesn't coincide? Let's see. Let's see.
Well, I guess like A intersect B would be the same, but then on the bottom would be
Right, but you have to divide by the probability of B. Like,
yeah.
I mean, if you look at the formula, I mean, we can start with the formula just to kind of like make it clear that they're not the same, because the numerator is the same, right? But you know, but then the probability of B, you know, you then this one gets divided by the probability of B. I'm just thinking whether in this example, uh, what is what does the conditional probability correspond to, in this case, if you're given B, that means that it had two ones, and then yeah, it's still kind of like the same singleton. But yeah, there are many other examples where like uh I mean, okay, these are like 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 extreme cases, like or you thought like
Is there like, would there be any relation between them? Like how if we take the cross product and we flip the terms, it's a
oh no,
negative
there
cross
is a
product?
relation which is a Bayes theorem, which I'm about to write, but like just to
Yeah.
kind of like give a silly, I'm just trying to give like a silly example with like uh oh, okay, yeah. Like like if you had if you had two coins that you roll, right? And like the possibilities are heads, tails, heads, tails, heads, right? And then tails, tails, right? What could be like a Mhm.
P of A given B here different from P of B.
Already in this example you're saying?
It's 1/4 versus 1/4.
Oh, right. Oh, yeah, because I'm just looking at the intersection. I feel so silly now. Yeah, I was just looking at the intersect V. Yeah, no, you're right. Like, so in this case, right, because the probabilities of the sizes are, oh, yeah, I'm glad they, right. Okay, thank God. I'm glad you noticed this. Okay, let's say that every string happens with the same probability, right? Just to make our life easier, right? So there were 8 possible strings, right? So the probability, you know, yes. Whew, thank you. Okay. Right, so the probability, if probability of each string is 1/8, right? Right. Then what is the probability of A? The probability of A, there were like four things inside of A, right? So it occupies half the space, right? So the probability of A would be 1/2, right? And the probability of B would be, okay, now I feel good that I chose like an even number, like two numbers of ones, because now they do have like different probabilities, right? That's why I was getting confused. So the probability of B, right, like there are only three strings with two ones. So the probability of B would be 3/8, right? And yes, and then now because those two are different, right? Like then the conditionals are like, you know, right? What would be the probability of, but the intersection, right? Like the intersection is the same in both cases, right? So the probability of the intersection, it's just one, like like the probability of this x4, which would be 1/8. Oh, let's write this as 4/8 so that the 8's cancel more easily. Okay. Yes, and then what are the conditional probabilities? Oh, and then yeah, we can do some theorizing about what this means. So, right, the probability of B given A would be 1/8, right? It's always the probability of the intersection divided by the probability of A, which is 4/8, right? So the 8's cancel, and then you get 25%, right? Or 1/4. Whereas the probability of right, what the probability of A given B would be 1/8 divided by 3/8, and then that is 1/3, right? Which is what you were saying, right? And that makes sense because, right, like there were, if there are this is how you should think about this. There are fewer strings. There are fewer strings with just two ones, right? So it is more information. You get more information if you know that your message had two ones, because there are only three candidates, right? And each of them is equally likely, right? So whereas here you're being told that your string is one among four ones, right? So that is less information. So that's why this one has like kind of like less weight, less probability than the other. Yes.
The way I like to think about it, like, um, probability of like any event A is like just the cardinality of the set of A
Right.
divided by the cardinality of the universe.
Yes.
And if you like work it out, the universe is cancelled. So
Right.
probability of B given is just the number of elements in A percentage B divided by the number of elements in A.
Yes, that is good as long as which is what we're doing here, where like you can think about it in terms of cardinality or the size of the sets, if the you give like equal probability to each outcome, right? Yeah. So in that case, it just really is like counting, it's just like literally counting, and that's like a good, but that's always like a good like mental picture to have in mind. But yeah, like kind of like in more generality, right? In more generality, if you can kind of like divide them both, right? I mean, if you use a formula, you can divide the probability of B given A divided by the probability of A given B, right? And if you work it out, like, the intersections cancel. Well, let me just write all of it. So like, like it's, and you end up getting the probability of B times divided by the probability of A. So that does give you a general relation for the probabilities. So it says the probability of B given A is the same as the probability of A given B times the probability of B divided by the probability of A. Right. And I said that the base formula, if I'm not mistaken. So like you can kind of like reverse the, like, like they're not quite the same, but they are related by if you think about the probabilities as in terms of the relative sizes, right? Like it depends, the ratios of the conditional probabilities are kind of like, related to the ratios of like the total probabilities of the subsets.
And if the probability of B was equal to the probability of A, then it makes sense because the conditional probabilities would be the same.
Right. Like if the probability, yes, like if B and A occur with the same probability, then yes, like the conditional is the same. Yes, in that case. No, but
Hmm.
like where this is kind of like interesting is like in these problems about like you're being tested for like a disease, like the false positives and the false negatives. That's where it really gets like fun, like what is the probability, like you get like a test for cancer, like that it will tell you whether you have cancer or not. So what is the probability that you actually have cancer if you tested positive for cancer versus like like the probability that if you had tested positive for what would be the reverse? That you would test positive for cancer if you have cancer. It's not the same because like like the tests make mistakes, right? So they're false positives or false negatives. So that's why like and that's kind of like very useful. I mean, it's like a useful thing to if you take probability, you learn all those things. I'm just kind of giving you the basics for what we need, but yeah, it's kind of like a rabbit hole you can go into because it's like a very useful thing to know. But right, like that's what I was trying to remember, like these examples like of medicine, because they're really, like have like real life consequences when you get like a diagnosis, like that people don't really understand like what those quantities mean, right? So like they're giving some numbers and they don't know what that really means. Okay. Whew. So that is for now what I wanted to say about conditional probabilities. Now comes the joint distributions. Okay, and that's where we go back to matrices. Now this is where matrices come again. Okay, and like like the idea is kind of like pretty intuitive. So here you just think that the outcome space is kind of like for example, you could think that it's being characterized by two particular properties. So now the outcome space or features. I'm trying to use some terminology that feels like more like data sciencey, right? Like so here's like a very silly example, but it's kind of like useful just to kind of like have like a mental image. So imagine like you have like a supermarket, but it's kind of like a very simple supermarket. So they only sell like fruits and vegetables, right? Uh, which I'll call fruits F and vegetables, I'll call them V. Okay. And they those like fruits and vegetables again, it's very poor supermarket, so like they don't have many varieties, so they only come in three different colors. Like there are only three possibilities for what the color, you know, uh could be of like which I'll call the colors red, green, and purple. I'm just trying to make sure like there are no letters being repeated like for like the first name so that it's not like a mess. So like you could imagine what is the outcomes? You could imagine that you are going to kind of like keep track of like what the customers buy, right? And here you can have like more like a frequentist point of view in probability. You just kind of like keep track over a couple of days, of what they're buying, and then kind of like the frequency, like like how many times they buy like a red fruit over the total number of purchases. It's kind of like an approximation for like what the true probability should be of 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 that purchase. So like you can kind of like think about there are like six possibilities, right? Which is that you buy a fruit that is red. Well, let's write it like yes. Yeah, a fruit that is red, or a vegetable which is red, right? Or a fruit which is green, or a vegetable which is green, or sorry, a fruit which is purple, or a vegetable which is purple. So here, like kind of like you see, like the possible outcomes have two features, two characteristics, which is why I'm using like an ordered pair. And so you could imagine like assigning a probability, to each of those outcomes, right? But it's kind of like makes more sense to label the outcomes in terms of like the individual characteristics, right? So if you thought of red, green, and purple as being like, X1, X2, X3, and the fruits and vegetables as being Y1 and Y2, you know, then kind of like in more like the traditional notation, what I'm writing here is like, kind of like a Cartesian product, right? Like of X cross Y, which is just X1, Y1, X2, Y2. Oh, sorry, let's just go in order. And then you could imagine like the probability just being like, like the probability is P of ij, which is the probability the customer buys fruit, well, like item J with whose color is I. Is that making sense? Kind of like the setup of the prep of the situation. So in this case, like again, there are three colors. I is giving you the color. I is the color index. J is the I, like the food type, fruit of or vegetable. So, you can represent this kind of like in a very natural way as a probability matrix, right? Which is called like a joint probability matrix, you know, which in this case is what? 3 by 2, right? So again, color goes this way, and then food type goes this way, right? So it's just P11, P12, um, P21, P22, P31, P32. And in this case, what happens if, well, their probability, so each entry is non-negative. And then if you add up all the entries of the matrix, you should get one, right? Because those are all the possible outcomes. So here, Pij is always is between 0 and 1, and the sum over I and over J, right? There are two sums, right? If you add up all the coefficients of the matrix, that should be 1. Because there's 6 outcomes, it's just that I'm kind of like identifying the outcomes by 2 features, right?
What can you do differently with the probability matrix compared to just like having a table of what each probability is?
Well, that's what I'm about to do in a moment. So for example, okay, here's something you could, like, we might as well say it now. Like here's which I had talked about before. Um, what if the rank of this matrix is 1, right?
Yeah.
Here's like a question. So here's a question. Okay. Well, if the rank is 1, if you remember, that means that it is a tensor product of two vectors, right? Like the matrix P would be just a tensor product of two vectors. Let me call them strategically P sub X. Let me see which, okay, how I need to, this is going to be a 3 by 2 matrix, right? So, well, I don't want to kind of use a lot of notation. So this is going to be a vector, which I'll call P, and a vector which I'll call Q. But let me see which one is which. So this one, remember like the formula for the tensor product of two vectors is P times Q trans P times Q transpose. Let's see if that's like the one. Right. Let's see. I'm thinking of the vectors as being column vectors, right? So maybe P would be 3 by 1. So I'll call it P1, P2, and P3. And then Q would be Q1, Q2, right? And so let's see if this is making sense. So like this vector is 3 by 1, and Q would be Q transpose, right? Would be 2 by 1. So the size sorry, like Q transpose would be 1 by 2, right? So the sizes to match up, right? So if you work out what the tensor product tells you is that P11, P12, P21, P22, P31, P32, right? If you do the tensor product, it's just like the individual multiplications, right? So it would be P1 times Q1, right? And then P1 times Q2, and then P2 times Q1, and P2 times Q2, P3 times Q1, and P3 times Q2, right? Is that making sense?
Yeah.
And well, but that is actually, when the two properties are independent of one another, right? Like that is actually how you compute the probabilities for like, for for the two proper like, this is essentially saying that the features of having like the food type and the color are independent features, right? Like this is like the independence condition, so because like independence, like I don't know if everyone has seen like what does it mean when two events or two outcomes are independent, but like the idea is that, like for example, like when you roll maybe I should do it with a coin flip, right? As an example, if you do a coin flip, right? If you're flipping a fair coin, you could have like a you know, you can kind of like have like a similar setup here where it's like the probability of getting heads, the probability of getting like let's say I'm flipping a fair coin twice, you know, the probability of getting heads, tails, the probability of getting tails, heads, right? And the probability of getting tails, right? And if the coin, if the when you're tossing the coin that it is independent, the second time from the first one, right? Then, like the probability of getting heads is just like the probability of getting heads times the probability of getting heads. So, this would be the probability of heads times the probability of heads, which is like one, it would be, each of them would be 1/4 because each of those probabilities in the fair coin is 1/2. So what I'm saying is that having the rank of the matrix of this joint probability matrix being 1 actually tells you that that the features X and Y are independent of one another. Is that making sense?
Yeah.
So if P has rank 1, so kind of like the rank is a measure of how much correlation there are between the different properties of the variables, right? If P has rank 1, then the features I and J are independent. So for example, oh, sorry, yes. So can you repeat anything that's not rank one? Anything that's greater than right. If the rank right, like it's very useful to write it as a contrapositive. So if the rank is greater than one, there are correlations between the features, right? Like the yes, right. So if rank greater than one, the features are correlated. And again, I'm using like the terminology kind of like of features just so that it sounds more like data sciencey. But like the okay, here's like one thing. Like you could imagine, for example, that let's do something this like something this.
In
Uh-huh.
in this context, like I know we define rank as like a whole number, but I recently saw something about how like you can define dimensions as like non-whole numbers like 1.6. So is there possible you can define a rank as like a non-whole number in the context of how it relates to the correlation between these dependent or independent probabilities?
So right, there are these fractional dimensions, but I don't know whether someone has kind of like done like a kind of like I suppose like you could try to find like kind of like a fractional version of rank. But yeah, like at the top of my head, I have never like kind of like seen that formula, but
Oh, okay.
I have never read like too much about like, like, I mean, also it depends on what you mean. Like, I mean, for example, there are
It was
fractals,
like a random thought, just like
but they're like, for
yeah.
example, fractal dimensions. Like, you can think
Yeah.
like a fractal dimension, uh, but things of that sort, but you have to be careful then, like, whether like how you want to use it to kind of like for the rank of a matrix. But but like for example, there is something you can do. Okay, there's something called the a spectral dimension, which is kind of like right, like that actually happens in quantum gravity, but that's like a different story. I get a different thing. But like where you say like that, for example, the dimension of space-time is 2.4 or something like that. But that uses like as some the spectrum, like the eigenvalues of an operator. But that's an entirely different thing. So yeah, I suppose there could be kind of like a fractional rank, but for us, like rank will always be like a positive integer. Uh,
Okay.
uh,
Okay.
no, but what I was going like the example I was going to think about was kind of like imagine you know, like here's like a silly example. Like imagine that, okay, there are 12 months of the year, right? And then let's say that there are only three professions in the world, like physics, mathematics, or data science. Like, so like the tech, like other letters have one, and that's the only three things that you can study. So you could imagine, like, there's a joint probability distribution that is just like the probability that someone who was born in February like, and also it's like a math major, or like the probability that someone was born in March and it's a physics major or whatever. You can imagine like all the possibilities, right? Like there are 12 times 3, there would be 36 possibilities. And like it seems plausible that those features are independent of one another, right? They don't like on which month you happen to be born, like wouldn't determine whether you ended up becoming a math, physics, or data science major. But there could be other, but if you had like the same features, like math, physics, data science, and you have other characteristics, like for example, whether like you did a double major or something like that, then you could imagine correlations because maybe someone who studied like physics happens to get a degree in mathematics or something dumb like that. So all that I'm saying is that it's very easy to kind of like come up with examples where like or weight and height, many things are correlated, but
So
as
it can reveal like hidden connectedness.
correct, and that's kind of like when you do the SVD decomposition, well, I don't know, I don't think I will get today to the SVD decomposition. I'll just mention the marginal probabilities to be done with for today. But yeah, kind of like the idea is like with SVD, like, the singular value decomposition or principal component analysis, all this stuff can kind of like reveal hidden features because maybe like there are other, this is a little bit more abstract, but like you can imagine kind of like having like an axis, in this case, like an axis is kind of like for the color, right? And the other axis in is for like the food type, right? But you kind of like if you think about it, like what the SVD decomposition does is kind of like find important directions in kind of like in the joint space, where like the like the matrix looks like more simple. So like, if you apply that idea, which I'll do next time, to like a joint probability distribution, then you can read certain things up from it, or like discover hidden connections, like what you're saying. Yes, exactly. That's kind of like, that is the advantage of having you know using the matrix for mentality over just, oh, let me just write down like a table of values. And you can imagine how this also generalizes to tensors, right? Because what if instead of having two properties, you break apart the features, like, maybe you have like something with four different characteristics that you want to keep track of. It could be the color, like the food type, the country of origin, right? Like, and just to go with the food example, could be the color. Are you a fruit of a vegetable? What's your country of origin, right? And maybe something about the price or whatever. And then now you have a tensor with four indices, right? And then you have like a joint probability distribution for, that depends on four things, like in rank, like order four. And if the rank of that tensor were one, then kind of like the same idea happens here. Like that means that the properties were actually independent of one another. Yeah, like the only thing I was going to say, maybe to start wrapping this up, um, is that so, for example, they're interesting. Okay, so you have those six numbers, but there are interesting ways to add the numbers, right? So, for example, you could add those numbers row-wise or column-wise, and that actually gives you also useful information about. Um, I won't. I will finish this next time because I don't want to kind of like put that. But for example, like imagine that you added like this column. Okay, if you did P11 plus P21 plus P32. Okay. So what are you doing the sum? Oh, sorry, that was, oh my God, I wrote the indices wrong, right? Like, so this is P31, right? Okay, what is the sum over? That is a sum where like what's changing values is the color, right? Like the color index is like one that's changing values, you know. And the color index is changing values, but the food type has been fixed, right? Like what food type are we talking about here? We're talking about the first food type. The first food type was fruits, was it? I think. Let me just put like the labels here. This was fruit, vegetable, and then it was red, green, and purple, right? So here, like this one, oh, because it's always the index one for the column, that is always about the fruits, right? So these, right, it is actually because you kind of like you're adding over I, so you're losing information about I, like you're tracing out almost like that's another way of saying it, like the information that's coming from the colors. So these no longer depends on the color anymore because you kind of like took all the possible colors into account. So it's something information exclusively about being a fruit. So you interpret that as a probability that the customer would buy a fruit, and this is called like a marginal probability. So this is called like a marginal probability, and you would write this, for example, as P of F. Okay, this would be the probability that you bought a fruit, like for example. Right, because to buy a fruit, it means that you have to buy either a red fruit, a green fruit, or a purple fruit. So like all the possibilities, by adding them over, you exhaust all the cases, and then just like ends up like erasing the information about the color. So this is like the probability of just buying a fruit. Buying a fruit without interest, without any concerns about what color it was, regardless of color. Is that making sense? And then the other column, as you could imagine, the other color is kind of like the same idea. It would be kind of like the, but now what you're is related to the vegetable, right? So this would be the probability of buying a vegetable, right? And if you add it row wise, it would be the probability for each color, right? Like the first one would be the probability. But maybe I should kind of copy paste it. And that would be the last thing I write for today. Copy, paste.
Professor,
Yes.
if you took like the SVD of the matrix and then you looked at like the top K like sigmas to determine like which like has the most like effect on the matrix, then like could you claim like those features are the most like important that affect the probability outcome for something?
I mean, yeah, you just have to be careful because then I mean, yes and no, like mathematically speaking, yes. It's just like you have to be careful when you're trying to I mean, because you know, what does it mean to have like if you have a vector in this space, right? Like this is a space of like of color and food type, right? Like you have to
Yeah.
imagine, you have to give it like an interpretation for what is a vector. What is a direction at 45 degrees, right? What does it mean to be kind of like at the same at equal angle from being food or color, right? So like it is a bit more tricky than that, but yes, uh I
Right.
I will do something about the SVD next time, and it's related to these marginal probabilities, actually.
Like
Uh-huh.
Like, what if you were trying to like maximize, like make a decision on like what feature you wanted to boost in your store to maximize people just buying food? So like, could you use that to figure out which is the best one?
I mean, it is connected to that, but I'm just saying, like, you have to be more careful with that because, like, you know, yes, like, if that, like, for example, you know, if you did like an SVD, right, and you imagine like kind of like one of the eigenvector with the largest singular value being closest to red, right? Then
Mhm.
you would guess that that means that right, like then red is kind of like like the color that customers are preferring the most, or like maybe red, red happens to be closest, to red and like like a vector happens to be closest to red and and like and the fruit like and the bean fruit or something like that. And so yes, like there are some connections there, but I'm just saying like, it like the difference between like the data axis, if you think of the feature axis versus like the mathematical axis, is that kind of like in mathematics, like when you just write X and Y and Z, you're thinking about both of them, all of them as being physical dimensions, right? So that has a
Yeah.
clear interpretation that what if one dimension is color versus the other one is food type, right? Like the geometry is a bit more tricky because, like you have to think a bit more carefully about what does it mean to combine, you know, things of like of a different nature, right? It's kind of like,
Right.
yeah,
Yeah.
but I mean, but you're not off the mark because obviously that's also why we have talked about SVD and other things because it does help you clarify the nature of that. What I will kind of like, all that I'm saying is that for now is that if you kind of like start with your, just to wrap up the idea, if you start with the joint probability matrix and you kind of like either sum along columns or sum along rows, that basically kind of kills off one of the features, right? Because you sum over the different values of that feature. So you get something that depends exclusively on one of the other, like on the other property. And those are called like marginal probabilities. I'll talk about those more in next time, because what happens is that if you do an SVD, then you can kind of like read off the marginal probabilities and some correlation probabilities from an SVD, but I'll mention how that works next time. Yes, like, I think this is a good place to end because we're almost done with that.
Okay.
Okay,
Yeah, that makes sense though.
okay, good, perfect. I'll see you. I guess I'll see you on Monday. You're coming in person, right? Uh,
Yeah, yeah.
okay,
I
Tuesday.
was just home because of for the
Right, right, right,
holiday.
right. Okay, okay.
Yeah.
Yeah, Tuesday, right? Not Monday. You are.
I'm still catching up on the last two lectures.
Well, you can ask me.
Because
Like,
everything.
yeah, I'll have office hours on Tuesday if you want to ask me anything. Yeah.
Okay.
Okay,
Okay,
cool.
that works.
Okay, I'll see you.
Um,
Then.
Is the assignments both due on Sunday?
I mean, you can. I have to start grading them, so you can start. So if you want to submit them later, I'll grade the first whatever, like the ones that were due much earlier. I'll grade those over the weekend.
Okay.
But not, you don't have to. Yeah, you can wait on after office hours on Tuesday if you want to ask me something about that for the assignment.
Okay.
Yeah, 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 yeah.
Yeah, I actually I had a question on one of like the
By the way,
proofs
the other
for
colleague, just in case, like I don't want to keep anyone. Yeah.
the one of the proofs for the second assignment, but I guess I can come to office
Yeah,
hours.
let's do it in person just because like it's easier to type things.
Yeah.
Yeah, yeah. Okay, no, no, but don't
Okay.
worry about that. Yeah, yeah, yeah.
Okay, thank you.
Okay, okay.
Bye.
See you next week. Bye.
See you next week.